So now that we know about functions, we're going to get into specific types. In this section, we're going to learn about linear functions, and the next one will be other types of functions as well. So a linear function just means that it's going to be a line. We can say a function is a linear function if for real numbers a and b, your function has this form. So it's some number times x plus b. Now, if this a doesn't equal 0, then the domain and range are both all real numbers. You can input whatever you want, and you'll get every single number as the output. In the case a does equal 0, then this piece would be gone, and you would just have your function is equal to b. So it's always going to be a constant value. You can still input whatever you want, but the output is only going to be the value of b. So that'll be a specific type of a linear function. Now the slope of the line passing through 2 points is going to be classified as m. It's our rise over run. Another way you might see this as delta y over delta x. All this does is this means the change in. So it's the change in y over the change in x. So it's a difference in y values over difference in x values. You just have to be consistent. This point belongs together. This point belongs together. You can't switch that order or you're going to be off by a minus sign. The only time you can use the slope formula, though, is when the x's aren't equal to each other. So that's going to be a different type of line that's not actually a function, but it is a line itself. So the slope of a vertical line is going to go up and down. That can't pass the vertical line test. That's going to be undefined because that's going to be when you're trying to divide by 0. Slope of a horizontal line is going to be 0 because there's going to be no change in y. So let's look at all these different possibilities. Here's all our different possible outcomes for lines. So in the first case, you have a positive slope because your y values are getting larger and larger. So if you think of it in our terminology we learned last time, this is always going to be increasing. In the pink case, the y values are getting smaller and smaller and smaller. So this has negative slope, so it's going to be decreasing. In this third case, it's going straight up and down. It's an undefined slope because it's a vertical line. Can't classify this as any particular things because this isn't a function, so you can't say it's increasing, decreasing, or constant. In the fourth and final case, that's when you have 0 slope because the y value isn't changing. It is a horizontal line. So in this case, it's always going to be constant. Okay? So let's go ahead and graph the line, and then we'll state the domain and range at the end. So I'm giving you this form right now, negative 4x plus 3y equals 12. That is not in the appropriate form that I can tell what the line is. I don't know the slope. I don't know the y-intercept. So if you remember our slope-intercept form, that's really this value up here. Slope-intercept is y equals mx plus b. So this value attached to the x is your slope, and this tells you where it'll intercept the y-axis. So what I want to do is I want to go ahead and I want to write this in that appropriate function form. I want to solve for y. So we'll go ahead and add 4x to the other side and divide by 3. So now I know this 4/3 is the slope, 4 is the y-intercept. To graph this, I should find some of those important points. I should figure out what the y-intercept and x-intercept are. So remember, that's where you set the opposite variable equal to 0. And it doesn't matter, you can use this equation, you can use this equation to solve for the intercepts. It makes no difference. For the x-intercept, I'm going to go ahead, or for the y-intercept, I'll plug in x equals 0. So you get 4/3 times 0, which is 0 plus 4. So our y-intercept will be the 0.04, which is exactly what we get here. But remember, the intercept is a point itself. For the x-intercept, we can use that first equation. So when you plug in y equals 0, this will be 0. You get negative 4x equals 12. And that tells us that x is negative 3. So our x-intercept is negative 3, 0. So if we want to graph this, we'll go ahead and draw our xy coordinates. You can do this a few ways. Since we did find those intercepts, you can plot those and connect the dots. You could start with that y-intercept. You can use the slope. Doesn't make a difference what you use. Let's go out 5 in each direction. So that's -5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So we could plot that y-intercept, which is 0, 4. So right here, your slope is 4/3. So you could go up 4, right 3. You could go, you could also go down 4, left 3. And here's the other intercept. And then you go ahead and connect the dots. So here's the graph of our line. Our domain is all real numbers. Our range, same thing. You can have any real value because the y's go on forever because of those arrows. Okay. Now let's go through this next line. We've got 3 plus x equals 0. So I don't have our y in here at all. So let's go ahead and solve for x in this case. We're told that x is always equal to -3. So if you do try to find your x-intercept, you would set y equal to 0, but there's no y. So we're going to intercept the x-axis at the point -3, 0. If I look for the y-intercept, you set x to be 0, but that just tells you 0 equals -3. So that doesn't happen. There's no y-intercept. So really, if you notice, this is x is equal to some constant. That's going to be a vertical line. So when you graph it, it's just going to go through -3 and continue up and down. Your domain is that input variable. X can only be -3. So you'd have the set containing -3 as your domain. The range, however, isn't any real numbers because it goes up and down. Y can be whatever it wants. Okay? So now let's go ahead and find the equation of a line connecting 2 points. So first thing I can do is I can find that slope. I don't know the y-intercept, but if we recall our point slope form, we can utilize that. So first, let's go ahead and find the value of m. We look at the difference in y values. So I'll pick the bigger one, 12 to go first, 8 to go second. But then I need to stay consistent with x. So I picked this point first. I've got to pick the 3 first in the bottom and then subtract the other x value. So this is 4 over -2. Our slope is -2. Now to actually write the equation of the line, we want to recall our point slope form. So that's going to be y minus y1 is equal to the slope times x minus x1, where this x1, y1 is just a point on the line. So right now we have our slope is -2, so that's our value of m. You can pick whatever point you want to plug in for x1, y1. I'll go ahead and pick the point 5, 8. So I'm going to go ahead and I'm going to take y and subtract the y coordinate, which is 8. That needs to equal the slope times x minus that corresponding x coordinate. So now we've got the equation set up. I just want to put this in proper function notation, which is in that in that slope intercept form. So let's go ahead and distribute that -2 to get -2x plus 10. Add the 8 over, and we get the line is equal to -2x plus 18. So our slope would be -2, and our y-intercept is the point 0, 18. So the point slope form is great for helping you write the equation of the line, but slope intercept is much better for actually graphing it. Okay. Let's try one more. Let's try the equation of the line between 5, 9 and -2, 9. So if we start by finding that slope, we're going to look at the difference in y values, and well, that's really just going to lead to 0. So the difference in x values doesn't ultimately matter. You're going to get 0 over 7, so the slope is 0. So really, if you look at this, the y value is exactly the same on each of these. So the y is constant, it's going to be a horizontal line. So the equation of the line, if you use point slope form, would be y minus the y coordinate is equal to the slope, which is 0, times x minus the x coordinate. This will just completely disappear. So you get y minus 9 equals 0, and our line is y equals 9. So it doesn't have a slope. The slope is 0, and then the y-intercept would be 0, 9. Okay? The last thing we're going to do in this section is talk about useful properties from lines. So the slope of a line is the ratio of the vertical change to the horizontal change. And what that does is if we have a function and we have a specific interval, we can see what the average rate of change is going to be. So the average rate of change of a function f on the interval AB will represent by m average. It's just the slope of the line that would connect them. So you look at the difference in y values over the difference in x values. Okay? So this applies to any functions, not just lines. If you have something we're going to learn in the next section, you can find the average value over that interval. So let's look at a specific real-life problem. In 1980, the number of high school dropouts in the U.S. was 5,085,000. By 2012, the number decreased to 2,562,000. We want to find and interpret the rate of change per year in the number of high school dropouts over this time period from 1980 to 2012. So what we want to do is we just want to find the slope of the line connecting these 2 points. Your input is the time, your output is the number of dropouts. So we're going to look at the difference in y values. So our first y value, 2,562,000, relates to 212. So that will be this point here. Your second y value is 5,085,000. And that corresponds to 1980. So in the bottom, I'm going to take 2012 and divide it by 1980. So if you look at those difference in y values, it's negative 2,523,000 over 32. And then also if we think of our units, the top is students or number of dropouts over years. So this is about negative 78,843 students per year. So what this actually represents is this number is the number of high school dropouts, how it decreased by. So that negative sign tells you the number is decreasing. So the number of dropouts decreased by about 78,843 students each year. So there were this many less dropping out each and every time. Okay? So what we're going to do in the next section, now that we've got our linear, which is one of our most fundamental functions we're going to use frequently, we're going to look at a bunch of different functions, their domains, their ranges, and then after that we'll learn how to create more functions from it and use that base function as our main starting tool.